Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show a CFD heat transfer analysis through a special type of nozzle using SolidWorks free surface technique. This is the model. For understanding the model in a better way, let us have a segmented view of this model. We can cut it from front end. You can see this is the model, right? See, the thing is, you can inject water from this side and water will come down through this small hole, and after coming through this small hole, it will be facing this surface. This is conical surface, and through this conical surface we are having very small openings, and water particles at a high pressure, it will be coming out from this small opening, and water at a high pressure will be coming out from the small openings, and here it will be converged. Water particles will be coming out from here and it will be entering through this hole, and next to that it will be passing through the small die openings, and here in this case you can see it is one converging location. Through the small die holes, water at high pressure will be coming out, and this is the exit location of these water particles, and from here we'll be injecting air. So there will be some kind of mixing of water and air at this location. So this is a heterogeneous fluid mixing through this nozzle. So we can see some kind of misting of water can be viewed at this location, right? So high pressure water particles will be coming out from the small openings, and where it will be accumulated at this location, and from the top of this one will be injecting air particles, right? So this is the thing. Now in the actual boundary condition, we'll put water particles from here itself. It can be injected from this location also. Actually, after passing from this location, it will be entering this small opening and it will be coming out from this conical face, right? Okay, so for initiating this flow simulation environment, we have to start with flow simulation here. Next to that, we need to start from wizard, and we're keeping the name of the project as project 2 by default. Next to that, we need to select unit systems, and as usual we're considering SI system, and from main parameters we're considering temperature in degrees Celsius. Next to that, we need to consider what type of analysis it is. It will be an internal analysis, and from physical features we're considering fluid flow, conduction, and as it is a heterogeneous mixing of water and air, so we need to follow free surface technique. It is time dependent, it is a transient analysis, so we're considering total time for this analysis as 60 seconds, and output time step we're considering as 1 second. That means after each 1 second we'll save the results. Gravity will be involved, and the direction of gravity is indicated by Y. So along Y it will be minus 9.81, and along Z it will be 0. Finally, it will be a free surface technique, as we are mixing heterogeneous mixing of water and air. Done. Next to that, we need to select different fluids, and from gas we are considering air, and from liquid we need to consider water. Water at a lower temperature will be injecting from this nozzle. Next to that, we need to select material. In this case we are considering stainless steel, so it will be stainless steel 321. Next to that, we are considering default outer wall thermal conditions and roughness, and finally thermodynamic parameters, it is 10135 Pascal, and temperature we are considering as 35 degrees Centigrade. Concentration, it will be initially it is filled up with air, and solid parameters are also it will be having temperature of 35 degrees Centigrade. Let us finish this. This is the computational domain. You can see we can hide this domain. As in this case we are having single fluid domain, because in the single domain we have to mix water and air, so fluid subdomains are not needed. And material we have already defined, it is made up of stainless steel 321, so no need of applying solid materials again. So we can apply our boundary conditions. Insert boundary conditions. We need to inject water from this location, or we can do one thing. Instead of passing water particles from here, we can pass it from this conical face also. It will be the same thing. So let us consider inlet mass flow rate of water particles as 0.2 kg per second. It will be passing from this conical face. And let us see the thermodynamic parameters and substance concentration. We're considering water temperature as 10 degrees centigrade and pressure is 251325 Pascal. Substance concentration, it will be water. So we can change it from air to water. So it is clear that from this conical opening, we'll inject water particles at a rate of 0.2 kg per second, and temperature of water will be 10 degrees centigrade, right? Go and check. Two more boundary conditions are needed. Let's apply the second one. Insert boundary condition. We have to provide air particles from this opening at a specific velocity. Let us select that location. From this location, we will inject air particles at a velocity of 10 meter per second, and substance concentration, it will be air particles. Go and check. Done. Two boundary conditions we have applied. Next to that, we need to apply another boundary condition, that is the atmospheric pressure at the exit location. So insert boundary condition, it will be atmospheric pressure at the exit location. Selected. Go and check. We got all the boundary conditions done. Next to that, we need to select goals. In this case, our aim should be to have temperature at the exit location. By the same time, by using a one equation goal, we can find the temperature difference between the atmospheric temperature and also the temperature at the exit surface, right? Let us select goals from here. Insert surface goals. It will be average temperature of fluid at the exit surface. So we can select average temperature of fluid, and the location is needed at the exit surface. Go and check. It is average temperature of fluid at exit. You can rename this one as average temperature of fluid at exit. Done. Another goal we want, that will be equation goal. We want to have temperature difference between the normal atmospheric temperature and also temperature at the exit location. So it will be from equation goals. Insert an equation goal. It will be obtained from simulation parameters. Let us see the boundary conditions or general settings. Environmental temperature we are considering minus, it will be obtained from that surface goal, average temperature of fluid at the exit location. This is the difference in temperature between atmospheric temperature and also temperature at the exit of the nozzle surface, and we can rename this one as temperature difference. Both the goals are defined. Now we can run it. We have already done this one in project 1. So not only we have seen the normal simulation, by the same time we have performed a one parametric studies of a design of experiments and optimization. Let us see the results from project number 1. Let us load the results. Results are loaded. First of all, we'll see different cut plots of pressure and temperature from different planes. Insert cut plots, and we want to see temperature fluid from front plane. Green check. We can edit this, and we can include vectors also. Green check. This is showing the flow pattern across front plane. Now we can do one thing. We can play it, or we can do something else also. Let us play these cut plots. This is flow particles, temperature fluid across this nozzle. Instead of temperature fluid, we can see pressure also. Pressure and velocity can be seen also separately. Let us see velocity. You see velocity distribution almost constant. It's not changing anywhere else. Only velocity is little bit higher at the small die openings. And next to that, you can see pressure also, right? Let us see pressure distribution through this nozzle. So pressure at the beginning level, it is little bit higher, because at the beginning we have provided water particles at a higher pressure. What pressure we applied, that can be viewed again from let mass flow rate. Let us view it. Edit definition, you can see what pressure we applied there itself. Mass flow rate was 0.2 kg per second, and from thermodynamic parameters you can see temperature is 10 degrees centigrade and pressure is 251325 Pascal. So it is 2.5 times more compared to normal atmosphere pressure. Okay. So pressure at the beginning it is high, but after passing through the small die openings, pressure is less. Let us clear and hide this one, and next to that we want to see surface plots. Let us show the surface plots through all the faces. You can see this is pressure distribution through the surfaces. At the starting point or before passing through the small die openings, pressure is very high because we provided water particles at a pressure of 2.5 times higher compared to the normal atmospheric pressure. And after passing through the small die openings, pressure is coming down. Now instead of pressure, you can see this one in the form of temperature also. Temperature fluid. Let us view it. You can see temperature. So when water particles were passing through this conical section, temperature was very less. It was in the range of 9.97 degrees centigrade. And after passing through these small die openings, when it is being accumulated at the free space, their temperature is in the range of green zone. It is in the range of 31 to 37 degrees centigrade, right? And also here in this location, you can see temperature is very less. Temperature is in the range of mixed zone. Bottom part we are having temperature in the range of 10 degrees centigrade, and top we are having mixed zone of yellow and green zone. So at different locations we are having different temperatures at the exit surface. Let us clear and hide this one. To view this plots in a better way, let us make the model completely transparent, right? The model is completely transparent. Now we can see the different particles, flow particles inside this nozzle in a better way. Let us see that surface plot again. Insert surface plot. You see that particles throughout this nozzle. down portion temperature is low little bit, right? Because from top side we are providing air, there will be some kind of mixing of water and air, and here temperature falls. So some kind of misting of water particles will be taken place at this location, right? Let us clear and hide this one. Finally, you want to see our goal plots. That means we want to have the temperature at the exit location. By the same time, we want to have the temperature difference between the normal atmospheric temperature and the temperature at the exit surface, right? So goal plots, insert goal plots, and let us select all the goals. We can transfer this one to Excel. This is the data. First one is the temperature difference. Initially temperature difference was 0, and you can see here up to 318 numbers of iterations, you can see the final temperature difference is 6.624 degrees centigrade approximately. And next one, the most important part, that is the temperature at the exit of this nozzle surface. Initial temperature was 35 degrees centigrade, and up to 318 numbers of iterations, final temperature is 28 degrees centigrade. So with this one you can conclude, but the things you have done something else, some design of experiments and optimization you have done, one parametric study you have done. Let us see what we did in parametric studies. We have changed the mass flow rate of water particles from this conical section. We have provided water at a mass flow rate of 0.02 kg per second to 1 kg per second, and based on that we have got a different scenarios. Let us see the scenarios what we got. You can see that at different mass flow rate we got different results. That can be seen from goals also here, right? You can see that when the mass flow rate was 0.02 kg per second, in that case average temperature fluid at the exit was 33.86 degrees centigrade, and the difference in temperature was 1.14 degrees centigrade. In the second case, when mass flow rate of water particles was 0.05 kg per second, in that case average temperature fluid at exit was 29.58 degrees centigrade, and the difference in temperature is 5.42 degrees centigrade. In experiment number 3, when mass flow rate of water particle was 0.1 kg per second, in that case that average temperature of fluid at exit surface is 27.63 degrees centigrade, and difference in temperature is 7.37 degrees centigrade. And in experiment number 4, when the mass flow rate of water particle is 0.5 kg per second, in that case you can see average temperature of fluid at exit surface is 26.76 degrees centigrade, and difference in temperature is 8.24 degrees centigrade. And in experiment number 5, when the mass flow rate is 1, we could not achieve the results, it was failed, right? Now with this data we can have some kind of idea that mass flow rate should be definitely less than 0.5 kg per second, because after that it is actually failing. From this data we can see that if you want to have some specific temperature at the exit surface, we can have some idea from this data. Like suppose you want to have the temperature in the range of 28 degrees centigrade, in that case mass flow rate of water particles will be in between 0.1 kg per second to 0.05 kg per second, right? That can be done also, but we are not doing that one. That can be done using goal optimization. Let us close it. Now with this one we will conclude our today's analysis. This is a very simple analysis. In this analysis we have provided water particles at a high pressure and lower temperature through this nozzle, and at the exit surface you can see some kind of space is there. In that space, when the water particles are being accumulated from the top opening, we are providing some kind of air, and here some kind of water misting effect is happening. So this is all about our today's analysis. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.